All right, midpoint Riemann sums. So we're going to do the one I left out, and we'll do a similar setup, 0 to 2 for subintervals. And this time, to construct the midpoints boxes, we're going to look along the top of the subinterval, and we're going to find the middle. And we're going to create the top of our rectangle at the midpoint of the subinterval's top. So right there about the middle and the middle. This is a better approximation than left, right, up, down, because part of each segment, subinterval, creates a box that is outside and then a part that is inside. So it's sort of like this card, this went over but this went under, and this went over and this went under. So it sort of creates quite a good approximation. All right, let us look at the midpoint Riemann sums for this example. So if this is 2, this is 1, 1/2, 1.5, or 3/2 for these points. But now we're interested in the points in between. So what falls between 0 and 1/2? You can add these endpoints and divide by 2. This is 1/4. This point right there is halfway between 1/2 and 1, which is 3/8, not 3/8, is it? 1/2 and 1. Oh, 3/4. Then halfway between 1 and 3/2. So we've got 4/4 and 6/4. So halfway in between is 5/4. And halfway in between 6/4 and 8/4 is 7/4. So these numbers will be evaluated on the function to find the heights of these subintervals, these rectangles. So we're going to get the width of each one is still 1/2, but the heights are found at these points. So 1/4 plus 1/2, and we're going to put in 3/4, the function evaluated at 3/4. That will get us the height right there. Plus 1/2 times the function evaluated at 5/4, and lastly 1/2 times the function evaluated at, I did 1/4, 3/4, 5/4, I'm up to 7/4. So that's the midpoint Riemann sums. All right, let's do an example that will show how this works all the way through to some numbers. So let's say that the function is y equals x cubed, and I'm interested in the area between 0 and 2. That seems to be a nice one to work with. And we will stick with the 4 subintervals. It won't always be that easy, but you'll always be able to calculate whatever. So 4 subintervals, if it was 6, you could do it. Let's set this up as left Riemann sums. And we're going to recall that we're going to look at the left side of each subinterval and create a left box from that left side. Oops, so I went and drew right. Okay, that's not too smart. All right, let me call this right. I'm sorry. Right Riemann sums, so I don't have to erase. All right, so this is the right side. Come on. I know it's 10:15, so you have to give me more grace. All right, right sides of the boxes are going to help us find the heights of these rectangles. So I'm going to do 1/2. I'll start with this one. it's 1/2 in width, 1/2, and then the height of this box, which is a right Riemann sum, is going to be calculated at 1/2 right here. Then go up and hit the curve and find the value by putting it in y equals x cubed. So I'm going to cube 1/2. So this is the width, height, done this one. The next one is 1/2 in width. Its height is when we put in 1 into the curve, x cubed. Then we're up to 3, then I write 1, 1.5, 1/2, 1, 1.5, so that's 3/2. 1/2 times 3/2 cubed. And last box is going to be putting in 1/2 times 2 cubed. Alright, I calculated all of that earlier and it came up to a number, and that number is 6.25. Alright, this would also be the upper boxes for this kind of curve. So the upper boxes and the right curves are the same for this example, 6.25 square units. Alright, now we'll do the same one and we'll do the left sum. Alright. So I'll draw it again. Y equals x cubed. 4 subintervals. 1/2, 1, 3/2, 2. Again, this time, since we're doing the left ones now. Left Riemann sums. We're going to look at the left side of each subinterval and create the boxes from there. Notice these in this case are the same as lower. Alright, going across, we get no height from this one, so no area. So a 0 for that box. This one is 1/2 long and it's 1/2 high evaluated in the function. So it's 1/2 times 1/2 cubed. Then this, so we've got this and this. Now I'm going to put in 1. Well, it's 1/2 times 1 cubed, and then 1/2 times 3/2 cubed. So I think that's the end. All right. So when I calculated that, I got 2.25. And so the true area will always lay somewhere in, because obviously this one's too low, is lower than the true area, and that one's too high. As you can see, parts of the boxes are too high. They go above the function here. The boxes are too low. They're coming out below the functions. So we know the true value is going to fall in between. We could increase the accuracy of those two numbers by increasing the number of boxes. So the more boxes, subintervals we have, the smaller this range will be, the closer to the true area. And we can get as close as we want by adding more boxes. All right, let me do a midpoint one, since that is a Riemann sum. Midpoint boxes. All right, on midpoint boxes, we have y equals x cubed, 4 subintervals. And we're going to go and grab the midpoint from each subinterval's top and create a box from that point. Excuse me. Alright, so This one time we need to know the points in between. We kind of discussed them earlier. So I remember that this one was 1/4. This one was 3/4. This one was, where were we? 1/4, 3/4. 4/4 is 5/4. I can do this. And this one is 7/4 for midpoints. So I know that this one is 1/2 long. And I'm going to evaluate the function at 1/4. 1/4 cubed. 1/2 times 3/4 cubed. And 1/2 times 5/4 cubed. And 1/2 times 7/4 cubed. All right. I don't really have that number. So I'm going to go and grab my calculator and get it and be back to finish up with trapezoids. So come back to me, part 3.